Everyone, welcome back. In this video, we are going to understand non-compartment models in pharmacokinetics. These models are very different from the compartmental ones we discussed before and honestly much simpler in some ways. So let's break it down. This method is also called as model independent method. Why? Because we don't assume any specific compartments in the body here. We don't divide the body into central compartment and peripheral compartment. Instead, we just look at the plasma drug levels and how they change over time and this and we use this statistical moment theory to describe them. It involves collection of data after administration of a single dose. This model is very flexible, okay? It can be applied to any compartment as long as the drug and the metabolite follows linear kinetics. It is based on statistical moment theory. It gives us information about how long the drug stays in the body. Now let's understand the MRT, mean residence time. So the MRT tells us the average time a drug molecule spends in the body before it gets eliminated. The formula is MRT equals to AUMC divided by AUC, where AUC, okay, AUC is the area under the curve, zero moment curve of plasma concentration versus time, while the AUMC is the area under the first moment curve, which is basically plotted by using concentration multiplied by time against the time. Okay, AUMC equals to integration 0 to infinity. So we are plotting by using concentration multiplied by time plotted against the time. So this helps us to understand how long the drug stays in the system. Next is MDT, mean dissolution time. This reflects how long it takes for the drug to dissolve in the body. It is calculated as MDT solid equals to MRT solid minus MRT solution. So MDT is mean dissolution time, MRT is mean residence time. This helps in comparing how a tablet behaves versus a liquid formulation. Now we have MAT, mean absorption time. It is also called as MIT, mean input time. This tells us how much time the drug takes from the time it is administered until it reaches systemic circulation. The formula is MAT equals to MRT oral minus MRT IV. This difference shows how much time absorption takes. Okay, depending on the absorption kinetics, the calculation changes. For the first order, MAT equals to 1 by Ka, where Ka is the absorption rate constant. For zero order kinetics, MAT equals to T by 2, where T is the duration of absorption. Now the applications include. It is widely used to estimate important pharmacokinetic parameters like bioavailability, clearance, and volume of distribution. This model is also useful in determining half-life, absorption rate, and first-order absorption rate constant of drug. AUC stands for the area under the curve. It represents the extent of drug absorption and is the one of the most important pharmacokinetic parameters. It is measured in units like microgram per ml per hour into hour. It helps us to understand how much drug is available in the bloodstream over time. And how do we calculate it? There are two methods. First one is trapezoidal method, then second one is pharmacokinetic parameters methods. In this method, trapezoidal method, we divide the curve into small trapezoids and we calculate the total area. In pharmacokinetic method, this method uses calculated values like clearance, dose, and all. So, AUC is a powerful, useful tool to estimate the bioavailability, drug efficacy, and comparing multiple dose regimens. AUMC is the area under the first moment curve. It is used along with AUC to calculate MRT. It represents the product of plasma drug concentration and time over the time. Okay. AUC formula is integration 0 to infinity CDT, while the AUMC formula includes AUMC equals to the integration of 0 to infinity into CT with dt. This values is especially helpful when studying absorption and clearance. Lastly, we have this trapezoidal graph. Okay, so how to plot it? This On this x-axis we have time and on the y-axis we have the concentration. For example, you want to calculate C3 AUC. Okay, so AUC includes T3 minus T2 into C2 plus C3 divided by 2. That's how you can calculate it. So that's it for the non-compartment models. This model may not look fancy with the compartments and arrows, but it gives us very powerful tools to analyze drug behavior in the body. In the next video, we'll look at the last type, that is physiological models, which closely represents actual organs and tissues. If you found this video helpful, do like, share and subscribe, and see you in the next video. Thanks for watching.